Good. Yeah, I successfully confused you. That's exactly my purpose. Yes. Okay. Yeah. Well, thanks for worrying about it. All right. So after some clarification on outside the box, what it meant, correct? We have exchanges between us and us and other, native speakers. And at the end of the day, we settle for this title. And so even the title is outside of the box, maybe. Yes. Yes. All right. So thinking outside of the box with collider experiment. Zhen Liu, I'll give you the. Okay, great. Thanks a lot for the organizer to arrange this, invite me to give this talk. It was a great pleasure for me to visit Florence for the first time. I really enjoyed it. As Roberto indicated, he continued his tradition of assigning impossible tasks for the speakers. And in the beginning, he gave me a talk title of out-of-the-box usage of muon collider. But later on, he decided it should be out of the box about muon collider experiments. So that is a very challenging task because we are all thinking about muon colliders and our collider experiments, but suddenly I need to be out of the box, outside the box. It's very complex English, but okay. So when we think about the colliders, high-energy colliders, particular the theme was really concentrated on muon collider, but it applies for many other colliders as well, right? We think about high central mass energy. We want to realize all the important physics drivers and see the physics around them and using them as benchmarks and study physics physics potentials and design our future experiments. But this impossible task that Roberto assigned to me is do not talk about any of those. So I have to talk about something differently. That's quite challenging. Okay, but I will take the challenge. Okay, let me use the muon collider as an example and give you some works that I can classify as outside the box usage of collider experiments. Right. So muon collider has high central mass energy and low backgrounds. We need to cool and accelerate muons before they decay, a very short lifetime, and also we need a lot of them, which is again typical for colliders. And this is a image schematic design of a muon collider that you have seen many times. Okay, as a typical high-energy theorist, we generally don't think of geometry matters for us, right? We just need to know how large the ring is and what's the central mass energy. Even how large the ring only matters if we want to run the ring ourselves for fun or try to impress our audience. But all of those matters if you are trying to think outside the box. Okay, so I'll give you the first example of outside the box that is called the neutrino slice, which is one of our recent works. Okay, so let's think about the neutrinos, and then we'll think about you will see what I mean by neutrino slice. Okay, for muon collider, as we know, we are accelerating unstable particles decays and showers, right? And the muon, before they reach interaction point, a fraction of them has already decayed away and generate electromagnetism shower. Okay. A lot of the busy stuff happening. People have to spend a lot of computation power to study the so-called beam-induced background. We find there are hundreds of millions of photons above certain very low threshold, and even with the timing cut, and also E plus and minus neutrons, etc. So basically, a very busy environment that affects how we design our experiments. Okay, so this is just a single muon decay, right? And just to show the better version of such a plot, I steal this one from Larry's talk, right? Again, a muon decay with magnetic field in it, right? So electron and curve and rich and shower, etc. A lot of photons in there, right? So the claim is will have happened about 10 million times per bunch crossing. So many things are happening here. Okay, so we have to design the shielding to get rid of those events and focus ourselves on this interaction point physics. That's our inside the box physics that we typically consider. Okay? And even more amazingly, by in Larry's image, okay, for a typical high-energy physicist event, that's what we think, right? Mu plus mu minus collide at the interaction point, produce something, clean event. We can record the particle, do the particle ID, right? And Larry has already showed us it's good. The real image will be something like this, even worse, okay, because of those beam-induced background. Right? But our work, or thinking outside the box, we claim we're missing some component in such consideration. Again, it's my recent work with my excellent collaborators. So basically, when we collide particles, mu plus mu minus, we have two bunches of muons, right? They collide each other with slight angles on the real design, right? There's some vacuum beam pipe. And those wedges are the tungsten shielding, as we mentioned earlier, to shield away the beam-induced background from electromagnetism. Okay? There's a halo of particles, right, from the muon beam, decaying and showered particles. So we are colliding them, right? We hope they get rid of those halo and will allow us to focus on this such high-energy collision. Okay, and just to get the sense of the rate, okay, per meter level for TeV scale muons, we have about 10 to the 5 of some decay, right? So if I have a straight section of the order hundreds of meters, I will multiply this by hundreds of meters. That is the number of muons from a bunch, right? A spill of muons, right? And the collision rate of how many spills pass by each other is about 10 to 30 kilohertz, depending on our muon collider design. So you multiply that number by this again, and then you know how much radiation dose you have. Okay, but did we forget about neutrinos? That's the question motivated our study when we try to think about it outside the box. Okay, and our viewpoint has changed while we are doing such a research. Okay, first of all, neutrinos cannot be shielded, right? At least in any manageable level. In particular, those are high-energy neutrinos, right? Is actually a part of the consideration for radiation hazard. You heard in this program that we actually don't want too much of them that affects the design. I will reflect some reflection in the later part of this talk. Okay, it is part of beam-induced background that we ignored essentially, right? Just in the previous all the cartoon images I show, the neutrinos just go away, right? From our consideration. Okay, we show the story is quite different. There exists a very unique flux of neutrinos that we need to tackle and utilize. Right? It has two folds. It is there, and I cannot ignore them, and we'll have to think about ways to handle them and use them. So let's see why. Okay. So we call these neutrinos called beam-induced neutrinos, beams. Okay, it's actually, as we mentioned in a few places, even in earlier talk by Sylvia, we actually want well-controlled neutrino sources, right? We want to know what's the energy distribution precisely. We want to know the flux precisely. I declare, because we know the muon beam so well, this is actually one of the most well-characterized neutrino beam we will ever build. Okay? That's already special. Okay? The flux normalization and energy dependence are really determined by my muon beam property, right? Really better than percent level. Okay, and muon decay is well understood. There's no hadronic factors, etc. Right? Muon decays into the neutrinos plus electrons. There's no non-perturbative physics I need to care about. This is a very local decay. Okay, there's no strong interaction involved, a large radiation involved. Okay. Comparing with the 10% flux uncertainty in traditional accelerators, I need near detector. I have uncertainties on this and that cross sections. This is really a fantastic neutrino flux. Okay, so it is fantastic just because we have fantastic muon beams. Okay, just to give us a sense of the energy we're going to have for such a unique neutrino beam. Its typical energy for a 10 TeV muon collider is larger than the phasor neutrino energy, which we already seen in recent years some interesting report about measuring neutrino cross sections in a particular energy range. Right, And it will be typically lower than the FCC forward neutrino flux. But again, about the level of well characterization, there's nobody else can compete with that. Okay, it is an unavoidable byproduct of the machine, and it's a built-in synergy between energy frontier and the neutrino electroweak physics, which I will cover soon. Okay. So what are beam-induced neutrinos good for? The first reaction, since I collaborate with my neutrino colleagues, we ask if I can do oscillations. Okay? It's interesting practice. You will see that because the neutrino energy is so high, the oscillation probability required the length scale is so long. Okay, you will only encounter the order one oscillation between Earth-Moon distance. So no oscillation program of the standard neutrino oscillation, right? But instead, if we want to do oscillation experiment, just as Sylvia mentioned in the talk before lunch, a neutrino factory would be more suitable for standard oscillations with low energy neutrinos. Again, it's a byproduct or something we are going to have if we have a muon collider in the earlier stage of the acceleration. Okay, it's all about how much we build a muon storage ring and how long a straight section we have and what's the auxiliary detector we put in there. But I think it's a very important and interesting opportunities, and our colleagues at Fermilab start to estimate what's the neutrino flux of the different accelerator rings that we have. Okay, so of course it depends on more on the finding of the upcoming neutrino experiment. I would argue, in particular, a case Sylvia mentioned, if the CP angle is small, we actually need a neutrino factory to determine that, because we need all good controls. And it can be also part of a muon demonstrated physics, because our energy is just in this, could be in this range if we decide to cool and accelerate the muons. Okay, so instead of the neutrino oscillation program I mentioned, okay, these free neutrinos from the beam-induced muon beam-induced at high energy muon collider is actually offering a high Q-square probe of fundamental matter in weak interactions from such a well-controlled beam. Okay, the beam energy are not necessarily new, but the flavor composition, sample size, precision, all of those components are. Okay, so here's a plot. We envision that we can probe the neutrino physics. Okay? Just a sense of this is a function of neutrino energy. This is a function of cross section, and again we have we have mu plus and mu minus. So we actually have both neutrinos and antineutrinos of both of the first two generations. Interesting geometric effect that I'll show you later on as well. But generally, you will see we actually have charge current dominance. There's a neutral current. So we have some very interesting deep elastic scattering, charm production, elastic scattering on electrons, and also resonant meson production and neutrino trident production. All sorts of effects can enter in this beam. Okay. So far, we are missing one thing, right? Here, we are just saying, oh, there's so many neutrino cross sections from a theoretical point of view. The question you would ask is, can we probe them? Right? Are these beams useful for them? What I will show you is the statistics of the beams are so high. Okay? We really should have access to many of them. It all depends on how we decide to utilize those beams by making more special detector designs. Okay, so let's before I talk about the neutrino slice, let me mention some other ideas has been mentioned in this program a bit. Okay, just like we have the phaser, we have forward facility, right? You can also imagine, because we need some straight section before the collision point to focus the muon beam, right? Then there will be a forward muon flux, a neutrino flux, that I could build a neutrino detector in some far forward location. Okay, so here's how do I say? Here's our simulation in the appendix, but just to give you a sense of how concentrated the neutrino flux is, right? The spot size about 50 kilometers away from the interaction point is still of a few meter level. Okay, so it's really 10 to the 9 neutrinos per meter squared per second. A lot of them in this forward direction. Okay, and definitely there's an interesting forward neutrino physics possibility, and I think there's a room for people to study more and more. Okay, but what we're question. Uh-huh. 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 Mm-hmm. Mm-hmm. I haven't, but how do I say? I think, as you said, just like a dual near detector, right? We need a few meter by few meter level of liquid argon to contain the shower and to do the physics. I think few meter by few meter is compatible with the spread of the neutrino flux we have, even at the 50-kilometer level, right? So just imagine in a real experiment, I wouldn't put the detector 50-kilometer away. I think 1 kilometer away is already pretty safe in terms of shielding away all the other standard backgrounds, right? Electric showering. So personally, we haven't investigated more, but I will mention a few other related works on this direction. Uh, yeah, 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 right. Yeah, right. Yes, indeed, there's an optimization one can do, of course, and the liquid argon needs certain depths to absorb the energy. Yeah, 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 right. Yeah, right. And also, as I would imagine, if we are in the future, we probably want to magnetize ones. So there's a real studies can be done. Okay, but what we are talking about is not this one. Okay, this one, okay, in some sense, yeah, we can do it. But for us to think outside the box, I'm going to point out there's a tangential facility we can imagine. Okay, so it's a circular collider. Okay, the muon decays tangentially, and there's a whole flux of neutrinos going to a tangential direction, and some of them will enter our collider detector as well. Okay, and that is non-negligible. In fact, it's so sizable that it becomes quite interesting. Okay, so in a related idea, a few months after our work, separately by Andre de Guia et al., they actually studying another outside the box idea. They say, oh, I have a muon, the anti-muon beam, so I have neutrinos and neutrinos and anti-neutrinos at the tangential direction. Maybe I should put detectors, away from the collider detector, just put it somewhere here or here in this radial direction. Okay, so where these two tangential beams meet. Okay, of course they are not detecting the neutrino collision, neutrino collision. They cannot. The flux is too small. What they are trying to say is this detector can detect both the neutrino interaction and anti-neutrino interaction, and they have a very distinguished, distinct angular behavior. So one neutrino detector can do both, and we probably have a lot of resolution on their physics. Quite interesting idea. Okay, again, is an example to show you we haven't optimized the interesting possibilities and designs, right? And for instance, this one can see both neutrinos, but neutrino and anti-neutrinos. This forward detector can only see one class. Okay, so it's a different physics. So and also for the muon detector, people again mentioned if I put a ton of the target mass, I can have some sizable neutrino flux along the line of the forward detector. Again, mentioned a few times. I think This is just the beginning. People really haven't fully thought about what's the neutrino opportunities and how to realize those neutrino opportunities at the muon colliders yet. Yeah. Yeah, you can do that. With this one, yeah, they look at similar ones, but it's somewhat different from what I'm going to talk about here. Okay, okay. So I'm thinking out of the back box in the sense that I'm not going to use a neutrino detector. Okay, I'm claiming back to the main detector. It is already interesting enough. In fact, there's many things we didn't know. Okay, so I think about this is tangential flux. I cannot shell the wave neutrino. I cannot make them away. Some of them have to hit my main detector. My main detector is a gigantic detector with large mass. Okay, it is actually a reaction, a neutrino detection experiment. Let me just give you a sketch. Okay. So this tangential beam will cross a narrow sliver of the out part of the muon detector. Okay, let me give you a geometry later on. Okay, so the interaction will be abundant and high energy because the cross section is linearly proportional to the energy and of the neutrinos, and the detector is gigantic. Our normal collider central detector is gigantic and massive. Okay, the rate is actually larger than anything we have about the neutrinos or about lepton colliders than we recorded in the lab. Okay, so for instance, okay, such neutrinos can go through this large charge current. Okay, I can just hit with some nucleus and produce a muon. This muon is energetic, TeV scale energy. Okay, low transverse momentum, but going in that direction. Okay, we can think about how to detect them, right? So induced a hadronic shower as well. Okay, when I hit with large Q square transfer, I really generate a shower of hadrons and a very visible charged lepton here. Okay, with large radius, that's very special. Okay, I don't have such thing from the primary collisions. I don't have such a thing from beam-induced background. This is a unique neutrino-induced topology. Okay. Okay. I can also have neutrino charge, electron neutrino charge current. I will have electron appearing with TeV scale energy in this region. Okay. So very, very special. Again, this is the electron appearing at, passing the tungsten shielding we can imagine for a normal electron from muon decay. So again, it's appearing electrons in my system. I can also have neutral current. I have appearing showers in the transverse direction. Very strange thing. Okay. Suddenly, there's some, in Lonely particle language, we call it the appearing, emerging, appearing tracks, or the low ENM jet, whatever. It's just some jet suddenly appear. So this will be some jet just appear with special angular directions. Okay? Very narrow cone, but large amount of energy. Okay? So many such events like this. Okay. So we consider. This is a qualitative analysis, right? Let's think about some quantitative statement. Let me put in some numbers, right? So we consider both muon collider 3 and 10 TeV mu plus mu minus machine. This again, we know we're thinking about analyzation cooling, and that's our standard muon benchmark. But also we consider the mu Tristan idea of mu plus collision. Okay, so I will also have such muon fluxes with neutrinos that are symmetric. Okay, about cooling mechanism we already discussed last week by Kitano-san. Okay, so what we did, I only have 15 left. Okay, maybe I may not be able to go to the second example of outside box, but let me give this box clear. Okay, so we consider the geometry of the 3 TeV muon collider and 10 TeV muon collider very nicely. Okay, it was very confusing to us what's the muon collider geometry, but the term actually publicize the models for the magnetic lattice. So we have certain level of close to reality thing, but I declare it's still not the ultimate one because we don't really simulate the beam. Okay, as you will see, naively for our series, we think muons just follow the ring, right? But this ring is not a perfect ring, and the non-perfect ring matters a lot for the flux we're going to consider. Okay, the collision ring collider point has a straight section, has a matching section, has a normal bending section, etc. Okay, and the beam itself has momentum dispersions and spatial dispersions. Okay? So those things have to be taken into account to give us some sense of what's the neutrino flux you're going to predict. Also, of course, the naturally muon decay has phase space, although it's boosted, but still generates a spread. Okay, so we write down a toy detector. For us, again, the event counting only matters on where you want the event to be and what's the density of the material. Okay, we again would like to work together with the real detector designs. Okay, so here's the neutrino-induced event at the main detector. Okay, I don't need to build a forward detector or tangential detector. The main detector you have to do for your physics, primary physics, are showered under this neutrino flux. Okay, this is 10 to the 8, 10 to the 9 per year, and a lot of them. Okay, question. Yeah. Very good. No. Okay. Yeah. So very good question. Very good question. So this is a detailed geometry. We can make this slide so special. Let me describe them. Okay. So the colored coding is the number of events of such neutrino events per year. Okay. The black one you correctly identify is the tungsten nozzle, right? You ask why half black, half colored. It is half black, half colored, because the muon decays tangentially, right? The decays from those muons for all the location only will fill up the upper plane, never the lower plane. So it's asymmetric neutrino-induced events. So this is real. Okay, yeah. So here, there is a crossing angle, but for this simulation, we didn't include that effect. But you can estimate the crossing angle will just make this one leaking into a negative y plane a little bit, right, with a small crossing angle. Okay. Okay, so you see very interesting geometry already. That's one point. Okay, so it seems like bad. Okay, 10 to the 9 events, neutrino events, TeV energy scale deposition per year. Okay, but it's also very nicely well contained in a single slice of my detector. So this is a YZ plane. This is a transverse plane, our typical ring of a detector. Okay, you will only occupy one single side. So all of those doses are in this line, along this radial line. Okay, again, because my ring is on a disk, the neutrinos only go to the larger of the disk. So this is a neutrino slice we declare. Okay, so that is an unavoidable flux of neutrinos, give me high number of events at my main detectors of my muon collider. Okay. Again, geometry matters, and detailed physics I will explain to you very interestingly. Okay, so we have the straight section and focusing magnets. Okay, there's some drift section. There's some bending magnets. There's larger curvatures, and there's a curvature matching section. Right. So you clearly you can see, if I ignore the angular dispersions of my my muon beam. Okay, the straight section will give neutrino in the forward direction, and also will fill this horizontal line. That's exactly near the beam pipe. I have a focused neutrino flux that we can try to utilize them in the forward direction, or it's also another series of events in my around my beam pipe. But where does the large radius region come from? Large radius region all come from the slightly bending one locations. That is 100 meters away. It's dominated by those contributions, but we will have them. Okay. And so we call this piece a neutrino slice, okay? And this highly dense yellow region, even higher number of events, we call it neutrino halo, right? It's really just a straight section neutrinos from my muon decays, mostly from a straight section. Its majority goes through the pipe, okay? You can do forward muon detection. It actually gave you some interesting physics as well. And some people encounter T-channel singularities. It should be calculated properly for this part of neutrino collisions in the interaction point. Okay, so let me just give you a number. Okay, the neutrino flux is actually really high. Okay, and my detector is so massive that we will end up having the total number of neutral and the charge current from those neutrinos. My detector is about 10 to the 10, okay, per year. 10 to the 10 events per year. What does that mean? That means about 1,000 events per second. If you recall, our collision rate of neutrino is 1,000. It's about 10K to a 30K. There's some mismatch in the calculation, but okay. Proper counting, okay, it's about 0.5 events per bunch crossing that we estimated. Okay, good. Mm-hmm. How was it normalized? We basically read off those properties, right? It's we can calculate how many muons per bunch, right? You calculate what's the effective contribution length that you have from this neutrino decays beam. You can calculate decay probability. You multiply the effective detection probabilities. Then you multiply the injection rate and clear repetition rate of the bunches. Yes, but that's each. Yeah, it's a per spot. You need to sum them up. Okay. 30. 10 to 20 to 30 kilohertz. Yeah. Yeah. Sorry. Maybe my number is wrong. Larry, what's the collision rate? 3 kilohertz. Not 30 kilohertz. 30 kilohertz crossing rate. Right. Okay. Right. Okay. So good. There's a factor of 10 that I need to fix. Okay. But I'm sure it's must because I forget some details. Okay. So, but again, there's our estimation. I think our paper is correct. Maybe my presentation or table is outdated. It's sizable. Okay. Order 1 collision, neutrino collision per bunch crossing. Sorry. This one only taking the H-cal and the E-cal region, which is only the large R radius. Okay, so if you take into a slightly the inner part, you will have more rate as well. But yeah. Because the mass, so there's the yeah. That includes narrow interaction. You're right. So narrow interaction is still away from beam pipe, but I have observable events from there. The tungsten narrow is actually a very good massive material for my neutrino interaction. Okay, so it's really sizable, but I would say this part of the rate is lower but cleaner. Okay, large R energy deposition in this neutrino slice. Okay. So here are some beam effects we induce. Just read out from the CERN's public lattice about some beam divergence in midi radiant. That's angular divergence and also dispersion, I call that. And also beam envelope, the size. We just naively Gaussian did it, but it's not the real beam dynamics. Okay, but we tried our best as series to get some effect into here. There's another interesting effect about straight section that we all know is a neutrino hazard. Okay, the high-energy neutrinos become a hazard for people living in the point, exiting point. So we discuss modulating the beam by slowly moving the accelerator components and trying to distribute the neutrino flux so to satisfy the radiation requirement. And we estimated these actually got broadened the beams that I show you in the neutrino slice by a centimeter level, or in the forward direction broadened by about tens of centimeter level. Okay. So it's actually an interesting effect, but doesn't affect much our direct considerations. Okay. So let's take a look at its a physics. Okay. So here's just look at the 10 TeV muon collider. Okay. We can think about what's the neutrino flux and what's the charged current induced charged lepton energy distribution. Okay. So neutrino is very precisely produced. Its energy distribution. There's no hadronic uncertainties about that, right? We really know neutrino energy distribution from muon decays like this. The charge current, dominated by low Q square, but still have all sorts of energy of charged leptons in the event. In contrast to the beam-induced background, which is very low energy, right? High flux but low energy. This is the neutrino-induced event. Charge current is really high energy. Okay, okay. And there's a strong correlation, in fact, even by our level of simulation, where the neutrino is interacting along this r direction, the radius of the direction, versus the angle of the outcoming with respect to the z direction. Okay, with the outgoing particles. Okay, charged particles. There's strong correlation. The reason is again, neutrinos energetic and dominated by forward scattering. The produced electrons and charged leptons are also going to follow the neutrino direction. So we know exactly what's the almost know exactly what's the neutrino direction, which we will know where the neutrino come from. We know exactly which beam element or which segment of the beam it comes from. So it's actually, this is neutrino slice events in a large R radius is actually a live monitor of my beam properties, okay? Which is very nice. Only have very narrow spread and angular and z spread in such a deterministic way. Okay, and about timing, again, I have some contrast to the beam-induced background. The neutrino, the beams are depend on your component, which are different radius. Means the neutrino coming from different part. Means they come at a different time. So time and the radius are strongly correlated. Okay, if I see those in the nozzle, it has all the neutrinos. But if I see them in a muon system with large R, I know they come from afar, 100 meters away. So I can know the time difference with respect to the bunch crossing. So it's really an interesting series of events in the recent geometry give us a lot of notable beam properties. I'm running out of time, but I want to mention a few more properties. For instance, in fact, we also know the produced neutrino, the charge current events, actually is energy distribution, and the rate have a dependence on the polarization. So these neutrino-induced events can also tell me the polarization of my beam. In particular for mu Tristan, where they can produce the highly polarized beam, it can be an interesting polarization monitor and the diagnosis objects. So let me just show you one example, a few examples quickly about what can we do positively, apart from the fact that it's already a quite interesting physics that we discover that will happen for muon collider. Let's just do a typical plot. As a function of neutrino energy, what's a cross-section? View it as a cross-section precision cross-section measurement device, only using these large R charge current events. So those are some of the previous measurements, and including the phasor measurements that interpreted such way. Okay. Well, we will have for muon collider beams for free at the main detector, so long as we can tag them. Ideally, we will discuss technical details later. Okay, we'll be able to measure this line. Okay, again, there are correspondence between the charge lepton energy and the neutrino energy is reasonably strong. Okay, so we've been wide enough that we think we can resolve. We have 10 to the 9 such events per year. Okay, so the statistical uncertainty is really negligible. So here, I just to show you the width, I inject a 1.5% uncertainty from beam properties, just to show you. We are supposed to really make this line very precisely. Okay, so it's the unprecedented neutrino measurement. In principle, we can also do a neutral current. All of them are all beam systematic dominated. In fact, again, that reflects the possibility that we can use those beams as a beam monitor. Okay, we can also do some charm neutrino charge current, etc. So statistics doesn't seem to be a problem for us. Okay, and we can also measure asymmetries, right? We can measure the asymmetries between this side of the events and that side of the event. Okay, those events there are some signs maybe missed here. Okay, but those event asymmetry of the neutrino beams interaction is actually proportional to Weinberg angle. In fact, it will give me a very nice Weinberg angle precision from neutrino collisions. People also interpret as non-standard interactions, effective radius, etc. Again, this is in some sense automatic. Once you have a great beam, you can do a lot of physics with it. Okay, precision physics with it. So you will be able to determine Weinberg angle to a great precision. Okay, again, you can see that's as a function of electron energy, depending on how much you deviate from the Weinberg angle benchmark we have, the differential rate will be different. Okay, so you can see you can use and also has polarization dependence. You can use those measurements to determine the Weinberg angle. Okay, so I don't have much time left, but I want to mention this neutrino slice summary. Okay, I think neutrino slice from beams provide a new program at muon collider detector. Okay, you view it from two perspectives. One is this is a large rate from unique neutrino source, really help us characterize the beam, and it may be a nightmare for our detector friends. Okay, it's a lot of energy deposition in a particular module. They worry about all sorts of stuff, but I think it's an interesting opportunity. We will be able to design a special detector with a special treatment in this slice. That is physically there. We cannot get rid of it. Okay, it's ultimately a new way to leverage muon collider to do weak scattering precision physics, DIS as the low X, and rare leptonic physics, and now neutrino physics. Okay, we need to take those into account, and this is again we tried our best, but it's our crude first look into those beams. We're thinking outside the box of normal collisions. And I think it's already bringing us a lot of surprises. Okay. I want to also mention this one. This is one word. Okay, thinking about outside box. We also know we inject a neutrino muon beam every 0.2 seconds, 5 Hz injection rate. That's because again our beam has a short lifetime. In some sense, I think we need to dump the beam, although a smaller fraction of the 10 to the 12 muons we have. But we need to dump the beam at those rate. But when we dump the beam, I would declare the beam dump is simultaneously a muon beam dump and a neutrino beam dump. Even that is an interesting physics opportunity. Again, we have to have it at the muon collider, so we should think about ways to utilize that. So I don't have time for the second one, I guess. Almost fast. Okay. Okay, let me tell you the main story, but I think, again, it requires something special that under debate, okay? Again, we are thinking outside the box. So here's how we produce Higgs boson at the muon collider. We are actually going to have 10 million Higgses, more than a typical Higgs factory, okay, which is about a few million, Okay, so we have a lot of Higgs, but we have a shortcoming in some regard that we all know the feature measurement of CEPC and FCCE and ILC is they can make an inclusive Higgs measurement and determine Higgs width. Breaks an interesting flat direction in our interpretation of Higgs physics. Okay, so there you can E plus E minus machine. I can use a spectator Z to do the recoil mass and get a Higgs reconstruction regardless of Higgs decay. So that gives you an inclusive measurement, determining Higgs width, or a threshold resonance mu plus mu s can do a scan and you can determine the width. But hydrogen muon collider seem to be unable to do this, right? And we produce a lot of the Higgs bosons via WW fusion. Okay, the neutrinos accompanying Higgs, I cannot make inclusive measurement. The second largest production for 10 TeV muon collider is actually the ZZ fusion process. Okay, so we can make all sorts of measurement, but we cannot determine the overall coupling scale or the Higgs width. That leads to an interpretation problem. Okay, I would not oversell it. I have a disclaimer in the backup. That's what the plot I made for muon collider forum report. Okay, if we let the width to be a free parameter, the muon collider Higgs precision fit is largely unbounded. Okay, so it's the finted shady region. If the width is not a free parameter, we can fit the precision very well. Okay, so can we get around this inability to determine Higgs width? Okay, so what we show with my student Pei-Ran Li, who is also here, is that we should make use of the sub-leading Higgs production channel of ZZ fusion by looking at these forward muons, tagging those forward muons, and do an inclusive Higgs measurement and determine the width. Okay, so recover muon collider program to make it interestingly compatible with other Higgs factory program for the Higgs width. Okay, so there's a lot of details about energy resolution, how much background we have, recoil mass. You naively think it's a usable observable, but it's not due to the resolution effect. Okay, so but nevertheless, the eventual story is muon collider being a lepton collider is actually quite clean. Okay, if I demand to tag those forward muons, my largest background is a bar background with ISR. Okay, that grid is still under control. So we can make such measurement and determine the Higgs width. Forget about all those details, but importantly, such an inclusive rate cross-section measurement requires forward coverage. I do want to tag those muons with rapidity of up to 6 to reach some great level of inclusive rate that will determine the Higgs precision at percent level. Okay, in detail, it's actually better than that in terms of interpretation. I will not go through that. So this way, to solve the problem of muon collider, we demand a new element outside the box of the major detector to tag the forward muons. So just to show you how powerful this is, before such a study, that's a global fit result. The shady region, the faint region is unbounded. With such a channel, it's bounded and make it a very interesting competitive program for muon collider. Okay, we don't need to go to details, but the demand for us, we have analytical control. The demand for us is I want to see the muons in the forward direction up to eta of 6, and that seems to be a very challenging task because I have physics I want to achieve, but the reality is we all know there's a radiations, right? A lot of beam-induced background. I exactly try to shield away using the tungsten nozzles, right? So the question is, to achieve such a great physics, I mentioned about Higgs width and etc. The leading other question is it feasible? Okay? In fact, I talked to different experimentalists and detector people. They split into campaigns. Half of them say impossible. Half of them say, maybe like think about it. So, but you can see, again, when we're trying to think about difficult tasks, we encounter some real challenges for interesting experiment, interesting physics and design, okay? What we really demand for the physics, we only need to require to tag the energetic muons. I just need to know there is energetic muon in this forward direction, okay? It passes nodal regions is not enough stopping power. I don't need to care about the energy loss there. It's not it doesn't affect my ability to separate signal and background. I don't need the great energy resolution, okay? So 10, 20, 30%, but all of them are fine. Doesn't change my result much. I also don't need large angular resolution. 50 milliradian is, should be good enough. I think it's a very strong case for R&D for forward muon detection. Just as, remind you about LHC, right? We actually tried a lot for the end cap physics and for physics because we try to improve the performance there to do VBF tagging. Muon collider will have the same issue. I want to do VBF tagging and disentangling. I will be able to tell apart from ZZ fusion, WW fusion, WZ fusion, etc. This physics, if I can do it, enrich my program immediately by many factor of many. Okay, it can also do other physics, invisible SIGs and etc. All sorts of other BSM usage. Just to give you a concept, I think outside this box of detector, the detector I need, okay, depending on where I put it, the required segmentation is those blue lines. I just need 3 modules, enough for me to do my physics. If you increase the angular resolution by a factor of 10, you will make this yellow dashed lines of segmentation of those. Okay, so again, it's outside the box, but it seems to me doable geometrically on performance, but I don't know how much background of radiation will pollute this. So I ran out of time. Here's almost my summary slides. I see Roberto is impatient. This is a beautiful plot made by Larry and Towa. Okay. In fact, this plot makes me think again about this gap. Okay. So the gap shows the bin interaction rate is here, right? Right. And the collision rate is over here. So but the physics digest events or VBF Z boson is there's a few order magnitude gap. So from a serious point of view, I wouldn't call this swamped by uninteresting stuff. With the first moment he showed me a much more weakened plot, I thought, no, it must be something here, right? So we added some points there, but I think it's I would declare it's unrealized opportunity. We have to think about what we can do. So for instance, if I want to further spread out this neutrino slice events, it will fill up different sub-process that we haven't measured before will fill out this region. But that's only one case. There are so many others. I think even the hadron events, there are some unrealized physics opportunities in there. So I think muon collider is very interesting. It has challenges and surprises. I hope I give you a sense of something we haven't thought about before. So when thinking outside the box of standard model BSM physics, I give you these 2 examples. But I declare, I'm sure there are much more to explore, and let's work on it. Thanks.
So regarding the 4, know what efficiency we need?
You mean if I put the forward detector, what's the efficiency?
What is the efficiency of our tagging has to be? Do you have a plot when you show the with and without? Is it like assuming like 100% and we're gonna get it, or
just to make sure we're talking about forward muon detector. So I think it does seem to me we don't need a very high efficiency because the flux is really high. Okay, so if I just as shown earlier plot, there's a lot of events even just have 1 ton of detector. Okay, so 1 ton doesn't mean all the neutrinos passing through will interact. I think it just means I think maybe a percent or sub-percent level of neutrino interact. But I forgot.
For muon.
So it's a totally different, non-neutrino. Okay. For muon efficiency, of course, we assume high efficiency. We think muon are really easy to see.
So, but do you have a study where it shows you, like, based on the efficiency, how much degradation you get in your fits?
Very good. So this one is actually directly scales as a square root of the efficiency degradation. Okay. So this is really statistical.
And you have to do both or one?
I would demand taking both. Taking one, there's a larger set of background I need to worry about, which we didn't simulate.
It doesn't look so complicated. Maybe I'm a naive experimentalist, but you have a nozzle, you have probably the cavern, you have a bunch of stuff that absorbs everything else but the muon. So I don't see why it would be difficult.
Very good. So that's exactly the non-trivial part. So imagine I put the detector here. You see, oh, there's nothing from here polluting my muon spectrometer. I should just see it. Yeah. However, the muon decays from this direction. There's a loss of energy into my muon detector. So how can whether I can?
Yeah, but you have a coincidence. I mean, these guys come continuously in time, and the muon that. Specific bunch structure.
Very good. Very good.
Coincidence because you want to see both.
Yes, yes. So that you see, I demand timing, right? So I probably need to segment this vertically as well, so I know it's coming to this direction. So that's our handle. So you are under constraint of possible. Great. Let's work on it.
Okay.
Field is glowing, right?
Yeah.
Yeah. The amount is dropping.
What we do with muon chambers and power calorimeters.
This is a lot more. This is energy coming in from the side, right? Yeah. No, I mean, like you integrate it every single event. You're talking EEV level energy deposit into that shield, right? So it's.
Yeah. Right.
Screaming at us.
Yeah, but I agree. You're thinking, oh, maybe this is a beam, right? Maybe I should add the shielding here, but the shielding has to be great. It may be very costly, large area, right? Large radius. Yeah. Yeah. Right. I think I just need a tag. I don't know enough what the different muon detection technologies. Some of them may be immune to the low energy depositions. Maybe have a reasonable direction on timing. I don't know. We have real experts here, but I think it's an interesting challenge if we can make it happen. Again, I want to emphasize the physics is just last you are all familiar with. VBF tagging, we did that for LC. We did so many upgrades for that to improve the performance, including missing energy and others, right? It will be as important, the muon collider as well.
So in terms of time, we have to say thank you again to Zhen. Thank you very much.